Hi, I'm Greg. I'm going to talk about some joint work with my collaborator, Jason, and my co-advisors, Kevin and James. Well, deep learning models often show superhuman performance on a wide variety of problems. They also often make systematic errors in a variety of ways. Sometimes they fail on marginalized groups. In face detection, they have poor performance on Black faces, especially for women. In object recognition, models sometimes fail on images from low-income households. And in speech recognition, models often fail on Black speakers' voices. But these systematic errors don't always lie along protected class boundaries or demographic groups. And sometimes models fail in other unexpected ways. Medical imaging classifiers are sometimes sensitive to small changes in the imaging hardware. Essay scoring systems sometimes give high scores to poorly written essays just because they're long. And visual question answering systems sometimes work perfectly fine for some questions, but fail as soon as the questions are rephrased. And identifying and fixing these issues is a really important problem for deploying these sorts of models. Thankfully, the machine learning community has a whole variety of methods for dealing with these failures. We have standards for auditing and disclosing performance on subgroups. We have tools for evaluating performance on intersectional subgroups. We have dashboards for interactively exploring how your model performs on all kinds of different breakdowns of the data. And we have optimization methods in fair machine learning for repairing these issues once you know that they exist. But what these tools share in common is that most of them require that you know what the failure is going to be ahead of time. You have to anticipate what this problematic subgroup is going to be. And some of these more unexpected failures, it can be difficult to know what's going to happen ahead of time. It can be difficult to anticipate the problem before you see it. And so the goal of our work is to take a trained deep learning model and surface the sorts of systematic errors that it makes without any prior knowledge or explicit labels of what these problematic subgroups might be, so that we can then feed these systematic errors back into the sorts of tools that I've been showing here. The way that we do that is we leverage a key fact about deep neural networks, which is that semantically similar inputs tend to have similar representations in the final layer of a deep neural network. And so what this lets us do is identify systematic errors by looking for regions of this embedding space where the model tends to get high losses, where it tends to perform poorly. And it turns out that these groups within embedding space typically correspond to semantically coherent groups of inputs. So this lets us identify systematic issues by looking directly at the model's embeddings. We aren't the first to look for systematic errors within models. In fact, there's a really simple and common approach that people take, which is simply to sort your inputs by their loss and take a look at what's going on with the highest loss examples. This might be familiar to you if you know about distributionally robust optimization methods, which treat this as an inner loop. They give more importance to high loss examples. But only looking at the losses tends to point out isolated problems or outliers that don't really have a whole lot to do with each other and aren't really a systematic error. And so more recent work has looked at ways of leveraging these hidden representations like we hope to. For example, Oakton Rayner et al. Called this error auditing. They fit a Gaussian mixture model to the embedding space, and they reported the clusters that had the highest losses. George by Sahoni et al. Does something similar. In their auditing stage, they look at the examples within each class, and they fit a Gaussian mixture model just to the examples in that class, and again, report the clusters with the highest losses. And while these methods tend to report coherent groups of inputs, they don't look directly for high loss examples, and they just sometimes happen to have clusters that have very high loss. So what we'd like to do is have a method that's a bit more consistent, that looks directly for the high loss regions in this embedding space and still returns semantically coherent groups. So we want to hunt for high loss regions like the first approaches, but leverage the internal structure of the neural net like the latter approaches. Here's how we do that concretely. What we do is we hunt for a contiguous set of points in a model's final layer representation, and we call this set of points a spotlight. So specifically, a spotlight is defined by a mean, which is its center, and a precision, which is you can think of as controlling its size. We allow for a sort of soft assignment of points into the spotlight. So a point that's exactly at the spotlight's mean gets a weight of 1. a point that's at the edge of the spotlight or outside of it gets a weight of 0, and points in between get weights in between. And then what we do is we look for a spotlight that maximizes the average loss, subject to one constraint. We don't want to just find a spotlight that has 1 or 2 examples. That wouldn't really look like a systematic error. So we add a size constraint. We require that the spotlight places a total weight of at least S points. And S is a hyperparameter that you can set to control how small or large the spotlight is, how many points it contains. In practice, to make this tractable, we replace this hard constraint with a soft penalty term in the objective function, and we optimize the parameters using Atom. We also have a simple method for fitting multiple spotlights iteratively. What we do is after fitting a first spotlight, we look at the examples that it identified, and we decrease those examples' losses in proportion to their weights. This encourages later spotlights to then find different areas in the embedding space and then different systematic errors. And so you can see that this method doesn't really require any knowledge of the model except for the final layer representations and the losses of each of the inputs. In the paper, we demonstrate this flexibility by running the spotlight on 6 different data sets. I'm going to show you 4 in this talk. We looked at image classification models. We looked at models on Fairface, Imagenet, and we also looked at some chest x-rays. But we didn't just look at images. We also looked at NLP models. We looked at sentiment analysis on Amazon reviews. And we looked at question answering on Squad. And we also looked at deep recommender systems on the Movie Lens movie review dataset. We also followed this up in the paper with a more quantitative experiment where we introduced synthetic errors into a superclass version of Imagenet and by adding label noise to one of the subclasses, and confirmed that the spotlight could find these synthetic errors. So here, for each of the models that I'm going to show you, we ran 3 to 5 spotlights, either containing 2% of the data set for images, where we could easily pick out the patterns by eye, or 5% for NLP or recommender systems, where it was tougher to see what the trends were. Let's dive in. First, we looked at Fairface. We trained a ResNet 18 to predict the perceived gender label that Fairface provides. And then we found 5 spotlights. I'm going to show you 2 of them here. The first spotlight on the top shows many images of profile views of faces. So these are views where the camera is sort of coming at the subject from the side. And the model seems to struggle with these. It seems to have a lot of trouble understanding facial features when it's not looking at them head on. The second spotlight that we found instead had many pictures of young children, of toddlers. We thought this spotlight was especially interesting because Fairface also, on top of these perceived gender labels, has age and race labels. And though the spotlight doesn't have access to these labels, if you break down the model's performance by each of the age groups, you can confirm that indeed the model performs poorly on the youngest age class. And so the spotlight seems to have identified successfully the systematic error that you would have normally needed labels to find. Similarly, we also show that further spotlights identify Black and East Asian faces, which again, you can confirm are indeed systematic errors using this side information. We also investigated the images with highest losses and from George's auditing stage, and we found that these were a bit more difficult to categorize. Next, we looked at Imagenet. We used a pre-trained ResNet 18 model from the PyTorch model zoo. Again, we ran 5 spotlights, and I'll show you 2 here. The first one on the top shows many images which contain a lot of objects in frame. These are really busy workspaces or public markets or things with a lot going on. And so the Imagenet model is pretty restricted in these cases to only output a single label, even though there are lots of different objects it might be able to classify. In a related way, the second spotlight that I'm showing here shows images of animals in foliage, where it's very clear to the model that there's probably an animal in there somewhere, but it's hard to tell exactly what the animal is. And so the model has to get high loss because it doesn't have a way of expressing uncertainty except for saying that it's not very confident in the true prediction. High loss examples on Imagenet were particularly uninformative. They just showed us a bunch of outliers that looked more like crazy labels than problems with the model. My favorite is a picture of a squirrel in a tree holding a piece of pizza, which of course is labeled pizza and not squirrel or tree. Next, we looked at an NLP model. We looked at a sentiment analysis model, which was based on BERT. And we ran it on Amazon reviews, predicting whether a review will be a 1 or 2 star review or a 4 or 5 star review. The spotlights here found first a large number of reviews that were written in Spanish, which the model had no idea how to parse. It was only trained on English text and consistently classified as negative. This was really shocking to us because the data set was purportedly monolingual and only had English text in it. So we were surprised to find that the model failed on these Spanish sentences because we didn't expect to find any in the data set at all. We also found that spotlights failed on long-winded novel reviews where it had a lot of difficulty following the long-range dependencies in these long paragraphs, and reviews about customer service where the model was very confident that people were complaining even on the reviews that where people were talking about how great the customer service was. George had substantial overlap with these spotlights as well. The high loss reviews here again appeared to just be issues with the data set more than the model. For example, one review said, "The background music is not clear and the CD was a waste of money. 1 star is too high," but the label is a 5-star review. Finally, we looked at Movie Lens, which is a movie rating data set. We used a deep matrix completion model. The spotlights here tended to find users or movies that had very few reviews. And so the model was very uncertain about what their reviews would be for in the future. And the spotlights also tended to contain movies that had 1 or 2 genres. In comparison, George's clusters were quite a bit different. They had very consistent ratings, which are what a subclass cluster looks like on Movie Lens, but had a less consistent spread of genres. So they were really spread out over different genres. We felt like both these methods might tell you something interesting about your model here. And so overall, I hope that I've showed you that the Spotlight is a very flexible and automatic tool for surfacing areas of weakness in models from all kinds of different domains. And while it's not going to fix your problems with your model overnight, I think that it fits in well into the broader feedback loop of that's common in model development and practice. Armed with our results, you might realize that you need to leverage additional data in training. On Fairface, you might realize that you need to train more carefully across to balance performance on different demographics. You might think of potential improvements to your model architecture. On Imagenet, you might realize that it's really restrictive to output a single label for each of the images. You might find harmful edge cases that you need to avoid outside of the model in deployment. You might have discovered that on Amazon reviews, you need to filter for only English reviews before applying your model. And more broadly, you might just discover things that you need to audit for more carefully in future development to avoid errors or regressions in the future. If this sounds good to you, there's an open source implementation on GitHub. All that you need to supply are your own models, embeddings, and losses on your data set. And you can use it for whatever purposes you like to audit your own models. Thanks for your attention.